NASA's revolutionary Juno probe is on a daring voyage to Jupiter. Its goal? To reveal the deepest mysteries of our solar system.
Everything we see in the solar system today is affected by Jupiter somehow, in the past or now. All the asteroids, all the planets, the moons, the comets, everything.
So in many ways, Juno is actually giving us a view into the history of our planetary system, even the history of Earth.
Juno's mission is risky.
Jupiter could eat the spacecraft like that.
But by diving perilously close to this monstrous world, Juno could change everything we know about our solar system.
If you want to know what's happening, you got to get up close and personal.
Independence Day, 2016. Juno arrives at Jupiter and gets to work. The probe angles its high-resolution camera towards this stormy world. Juno's snaps don't disappoint.
The images returned from Juno are just beautiful.
Suddenly you have this magnificent mosaic of this planet. As a human being, I'm like, oh my gosh, look at this, this is amazing, this is coming back from Jupiter.
These are the closest ever views of Jupiter, a world 500 million miles away. But we didn't send Juno just to take pictures. One of its main goals is to peer deep into Jupiter's dark heart.
One of the big questions we have about Jupiter is, does it have a core? And you'd think, well, of course it has a core. Like every planet has a core. The Earth has a core. Everything does. Well, it turns out Jupiter might not.
Knowing what lies at a planet's core allows scientists to wind back the clock billions of years to the formation of the planets. If Juno can reveal what lies deep within Jupiter, it could change our understanding of how the gas giant formed. If Juno finds a solid core, it could mean Jupiter first formed as a rocky planet like Earth, then kept growing. But if Juno finds no core, it could mean that Jupiter skipped the rocky stage and formed straight from a cloud of gas. Answering this question could shine a light on other mysteries too.
If we can figure out how Jupiter formed, we can figure out the rest of the story of the solar system.
So how do you probe down into the interior of a planet when all you can really see are the very tops of the clouds? Well, incredibly, you can use gravity.
As Juno orbits Jupiter, it can sense in its orbit tiny little variations in the gravitational pull of Jupiter.
As Juno speeds towards Jupiter, gravitational spikes tug at the craft. It turns out some parts of Jupiter are denser than others.
If Jupiter were some solid ball, then as Juno passes by it, as it passes very close above its cloud tops, the orbit, the trajectory, would be very smooth. But in fact, if Jupiter has layers, or places where there's more mass and places where there's less, then it's going to pull on Juno a little bit differently.
Passing over areas of concentrated mass gives Juno a speed boost.
So what they do is, the engineers back on Earth can basically just say, how fast is it moving right now? How about now? How about now? And you build up a map of where the mass is in Jupiter underneath the spacecraft as it passes around.
Juno's instruments begin to map out the heart of the gas giant, revealing the mysterious core for the first time.
What Juno found was this amorphous mass, a fuzzy thing in the center of Jupiter. It's not as solid as we expected if it were just a metal and rock core, but there is something there.
In the center of the planet, Juno detects hydrogen and rocky material dissolved and blended together. It's a type of planetary core we've never seen before. Astronomers are describing it as fuzzy.
We thought we were gonna find an avocado. Instead, we found a bowl of chili. It's a hydrogen fluid chili con carne.
So none of our models of the interior of Jupiter turned out to be correct. That means we have to go back to the drawing board.
One theory is that Jupiter didn't form from rocks or gas, but from tiny pebbles less than an inch wide, strewn across the early solar system 4.6 billion years ago.
These pebbles came together, they accreted to form a massive object that was the sort of seed, the core of Jupiter.
The swarm of pebbles clumped together to form one giant core, 20 times the mass of Earth. But these pebbles can't sustain this growing planet for long.
Eventually, we need to make a jump from those centimeter-sized particles up to really large things, like 100-kilometer planetesimals, to really kickstart growth of a planet.
As Jupiter grows, its appetite becomes insatiable. The cores of other would-be planets are drawn in by its immense pull and absorbed on impact, causing Jupiter's core to transform. Huge chunks of incoming rock are mixed up with gas and the pebbles that originally built the core.
We think that the core material that might have been there is actually dissolved and mixed in with the rest of the planet.
This mix of rock, gas, and pebbles leaves the core in a strange state, somewhere between solid and liquid, or in other words, fuzzy. Once Jupiter's core reaches a critical mass, its gravity starts sucking in all nearby hydrogen gas, building the iconic Jovian atmosphere and leaving the fuzzy core trapped beneath thousands of miles of thick clouds.
And that is what formed Jupiter as we know and love it today.
Juno's discovery of Jupiter's fuzzy core could rewrite the book on Jupiter's early years. But Juno's just getting started.
We haven't even scratched the surface of the number of mysteries there are.
There is more to Jupiter than meets the eye, as Juno's instruments begin to reveal a darker side to this giant world.
Jupiter's environment is one of the most vicious in the solar system, and that's because of its incredibly strong magnetic field.
And Juno is caught right in the middle of it. The gas giant Jupiter holds clues to the mysteries of our solar system. And in 2011, NASA launches a billion-dollar mission to uncover them.
3, 2, 1, ignition, and liftoff of the Atlas V with Juno on a trek to Jupiter.
To reach its target, Juno embarks on a 5-year journey.
Sending any spacecraft to another planet is going to be tough, but sending one to Jupiter is really pushing things pretty hard.
Juno weaves through the solar system with extreme precision. The craft battles violent temperature changes and navigates carefully through the asteroid belt.
If there's a fleck of dust in your path and that thing slams into your spacecraft, it can do significant damage.
1.7 billion miles into its mission, Juno finally nears its target. But the probe is hurtling towards Jupiter at 165,000 miles per hour.
Juno is moving really fast. It's one of the fastest spacecraft ever.
You need to go fast enough to get there, but then you need to be slow enough to be captured by the gravity of that planet. You need to get it just right.
Get it wrong, and Juno could slam into the planet or drift out to deep space.
To successfully get Juno to enter a stable orbit around Jupiter is almost the same as, say, shooting a basketball from London and having it land on the front of the rim in New York and just sitting there balanced. I could do it, but can NASA do it with Juno?
NASA has a neat game plan. Juno performs a backflip in space and fires its thruster towards Jupiter.
Everything is going smoothly. We're continuing to burn and change our velocity.
The rocket burns for 35 nail-biting minutes, reducing the craft's speed by 1,200 miles per hour. Finally, the probe achieves orbit around Jupiter.
Right on July 4th, during the fireworks, we just got into orbit. In many ways, we're firing our rocket motor. I mean, it is fireworks.
Safe in orbit, Juno turns its instruments to the planet for a critical part of the mission, investigating Jupiter's magnetic field. Deep below the stormy surface, liquid metallic hydrogen flows endlessly around the planet, producing a huge magnetic field. This magnetosphere stretches over 600 million miles beyond the planet, reaching all the way to Saturn.
If your eyes could actually see Jupiter's magnetosphere, and you tried to look at it while standing on Earth, it would look about as big in the sky as the moon.
And within this magnetic field, Juno faces an invisible threat.
Jupiter has an enormous magnetic field. It is so enormous in terms of space, but also in terms of power.
As Jupiter is bombarded by the solar wind, high-energy particles from the sun are funneled into deadly radiation belts, guided by the giant planet's magnetic field.
The magnetic field traps charged particles coming from the sun and circulates them around that system and just bombards anything in the vicinity, including our fragile little spacecraft.
Close to the planet, radiation levels are up to 30 times greater than inside the reactor core room during the Chernobyl disaster.
This is radiation. This is bad news. These particles, they would hit you, they would rupture your DNA, rupture your cell structures, and you would die.
This blistering radiation is bad news for the spacecraft too. The charged particles threaten to destroy electronic and navigational systems. But Juno has armored up.
It's not some delicate, beautiful, gossamer thing that you are sending to orbit Jupiter. It's more like a tank. You have to protect this thing, or else it's not going to last very long at all.
We've got a couple 100 pounds of titanium on the spacecraft just trying to shield us from what Jupiter might throw at us. So it is, in a sense, we're like an armored tank going into war.
Lightweight titanium is tough. Juno's half-inch thick shielding blocks 99% of Jupiter's vicious radiation. But even at this reduced rate, Juno can't survive the bombardment for long. So the craft sets itself on a unique orbit around the gas giant.
It actually has a very long orbit where it spends most of its time far away, and then every once in a while dives in, goes, oh, hot, too much, and then goes safely away to communicate and process, and then back in again.
Juno takes a mighty gamble, diving deep into these radiation belts to achieve one of its key objectives, mapping Jupiter's giant magnetic field. And as Juno swoops around the planet, it reveals something scientists had never seen before. Planetary scientist Dan Durda demonstrates.
We can use a pretty simple, even elementary school level experiment here of the structure of the Earth's magnetic field by shaking some iron filings across the surface of a very simple barred magnet with a north and a south pole.
Earth's magnetic field forms a perfect bubble around our planet, protecting us from solar radiation and cosmic rays.
I can get these little iron filings to come out here, and already I can see the sort of classic outlines of the north and south magnetic field lines that are coming out of our planet. The Earth's magnetic field is pretty well behaved in this way. It's what we call a dipolar field. It has a very distinct north magnetic pole and south magnetic pole.
Lucky for us, Earth's magnetic field is pretty stable. But new results from Juno suggest that Jupiter may not be so fortunate.
Jupiter's magnetic field is much more complex than this.
Jupiter's not going to play by those rules. Its magnetic field is going to do whatever it wants, and the generation of that magnetic field is so complex and so twisted and so wild that the magnetic field is going to have very, very strange shapes that we're just now beginning to understand.
When you look at the Earth, we have a fairly simple magnetic field. It's like a giant bar magnet with a north and a south magnetic pole. Well, Jupiter has that as well. This is called a dipolar field. It's got two poles. But it also has a third pole.
Juno's magnetic field map shows a north and south pole and a bizarre magnetic disturbance at Jupiter's equator.
And it's like Jupiter just sprouted a third arm, and that's kind of mysterious.
On magnetic field maps, north poles show up red and south poles blue. So scientists are calling this second south pole the Great Blue Spot.
Everyone knows about the Great Red Spot, but Jupiter now has a Great Blue Spot as well.
This magnetic disturbance reflects Jupiter's stormy interior.
You have these fast-moving winds blowing on the magnetic field, and they're actually shearing it apart and moving the field around.
It's not necessarily a storm, although it could be. It maybe is better to think of it as a magnetic storm.
Turbulence inside Jupiter could be twisting up the magnetic field to drive the Great Blue Spot and the deadly radiation belts that Juno must navigate through.
Unlike Earth, Jupiter is not really a solid mass for the most part, so all of its clouds and gases are moving at slightly different rates, and that actually makes the magnetic field that's generated be very variable and highly changing. For us to have a variable magnetic field like Jupiter does, the entire Earth would have to be molten. We really don't want that to happen.
With each orbit of Jupiter, Juno unravels more mysteries of this giant planet. But Jupiter's deepest secret could shine a light on our own origins.
If we want to understand the Earth and our place in the solar system, Juno has found a lot of those mysteries are locked up there in Jupiter.
The Juno spacecraft is uncovering the secrets of Jupiter, from its swirling cloud tops to its dark heart. But Juno's discoveries go beyond the gas giant itself. They could answer mysteries about our own planet too.
Jupiter is the key to the formation of the solar system, which means it's the key to understanding how the Earth formed.
Juno is actually giving us a view into the history of our planetary system, even the history of Earth.
4.6 billion years ago, a mammoth cloud of hydrogen gas and cosmic dust collapses, sparking nuclear fusion. From the resulting chaos, one star, 4 rocky worlds, and 4 gassy giants are born to form our solar system.
There's these distinct zones of the solar system, rocky and metallic in the inner part, gaseous and water-rich in the outer part. And even without thinking about that too hard, it kind of makes sense because in close to the sun, it's warmer. Out farther away from the sun, it's cooler.
But the Earth breaks the mold. Our planet has far more life-giving water than theories predict.
The Earth formed in a part of the solar system that you'd think normally should be probably pretty dry because it was pretty close to the sun.
Our planet is just 150 million miles from the sun, putting us inside what scientists call the snow line. Inside this line, the sun is powerful enough to evaporate water during a planet's formation.
Inside the snow line, the temperatures are high and there's a lot of energy from the sun nearby.
Too close to the sun, those gaseous and ice-rich materials just can't exist. They're evaporated away by the heat of the sun.
Our watery world should be a dry rock in space.
Understanding how water got to the Earth is so important because it wouldn't be there in the very, very beginning.
But Jupiter could hold the answer to this mystery. To solve the riddle of Earth's water, Juno aims to discover where Jupiter was born.
Understanding how and where and when Jupiter formed is critical because it has really dominated the entire evolution of the solar system. It's the biggest planet by far. It's the biggest thing out there that's moving everything around.
Any water in the early solar system could have been moved around by Jupiter's mighty gravity. So if Juno can trace Jupiter's history, that could explain why we find H2O where it's least expected.
We know that planets can move closer to the sun and farther out while they're forming and even after they form. So how do we figure out where Jupiter formed?
The key is how much water is locked up inside Jupiter.
If we can understand how Jupiter built a relationship with water, we can understand how water got distributed all throughout the solar system, including here on Earth.
If Juno can measure the water content of Jupiter, it will solve a 20-year-old mystery. December 1995. NASA's Galileo probe begins a fatal dive into Jupiter's atmosphere.
There are two ways we can investigate planets. One is to basically orbit the planet and look at it in every possible way you can. And the other way is to drop the probe in and actually physically see what's going on inside of the planet.
The Galileo probe was attached onto the Galileo spacecraft that went to Jupiter in 1995. It detached immediately upon arriving at Jupiter and went down into the atmosphere.
It was designed specifically to go down and measure the different cloud layers and get the composition down below where we could actually see.
The probe begins a death dive into Jupiter's clouds. Friction from the thick atmosphere pummels the spacecraft, tearing off panels and incinerating its parachute. 97 miles into Jupiter, the entire probe is vaporized, but not before it samples the atmosphere with its instruments.
When it did, it was able to measure the atmosphere around it and detect water. And the thing is, it didn't find any. And that's weird.
Everything was bone dry. So why in the world did Jupiter's atmosphere look dry?
If the results from the Galileo probe are correct, then 4.6 billion years ago, Jupiter formed closer to the sun. But that's not the whole story. 20 years later, NASA sends Juno to get a second opinion.
Juno is an orbiter, and so it is loaded with instruments and detectors to look down on Jupiter and try to figure out everything that's going on.
Juno doesn't have to risk its life to hunt for water. The craft peers through Jupiter's thick clouds using a microwave radiometer to detect H2O from a safe distance. Using these microwaves, Juno builds up a global map of Jupiter's water.
What Juno has found is, yeah, there's plenty of water in Jupiter. It's just that Galileo happened to hit a dry spot. But in fact, if it had come in almost anywhere else, it would have seen plenty of water.
Juno's findings may give scientists a clue to understanding where Jupiter originally formed.
It seems apparent now that Jupiter didn't form in its present location.
The leading theory is that Jupiter formed just beyond the snow line, the boundary between the dry inner solar system and the wet outer solar system.
But we find Jupiter is twice as far away from the sun as where that original snow line would have been. So this is telling us something interesting.
Jupiter may have wandered from its original position, causing unimaginable chaos.
As Jupiter moved around, things got hit and knocked out of the solar system.
It essentially scatters everything in its path. It's the biggest player, it's the biggest planet. Everything moves for it.
As Jupiter bulldozes towards the outer solar system, it slings ice-rich asteroids and comets in towards the sun and towards Earth.
Jupiter would literally, in some sense, have snowplowed into the inner solar system a whole wave of water-rich planetesimals that would have delivered much of our Earth's oceans.
Juno has helped answer why Earth is habitable, despite being so close to the sun.
So it was worth going all that distance, sending Juno all the way out there to get that closer look.
Juno continues to explore Jupiter's mysteries and its famous features.
There is nothing more iconic about Jupiter than the Great Red Spot.
And Juno reveals that this 300-year-old cyclone may soon vanish. Our solar system plays host to some epic natural wonders. The ice geysers of Enceladus, the giant rings of Saturn, the Martian mega-volcano Olympus Mons. But in July 2017, NASA's Juno probe skims the surface of Jupiter and photographs the most famous natural wonder, a fierce hurricane-like storm that's been raging for hundreds of years.
When you think of Jupiter, one of the most visually stunning, most iconic features of the atmosphere is that Great Red Spot.
There is nothing like Jupiter's red spot in our entire solar system.
As Juno soars over the Great Red Spot, it looks down onto a storm over 10,000 miles across.
This is the most extreme storm. The winds are blowing continuously at 400 miles an hour.
Earth's most powerful Category 5 hurricanes are less than half as powerful as the storm on Jupiter.
The Great Red Spot is the greatest hurricane that you've ever imagined.
But that's not all. Juno's microwave radiometer allows scientists to see through Jupiter's cloud layers for the first time.
Juno has instrumentation that's able to look underneath. So one of the things we did was we looked at how deep are the roots.
Juno peers down into the eye of this monster storm. It spots temperature changes that follow the storm's iconic shape, tracing the roots of the Great Red Spot deep into the Jovian atmosphere.
They found out that it goes down over 200 miles deep into the atmosphere. There's nothing like that on Earth.
Weather satellites circling the Earth show the greatest cyclones of our planet can reach heights of around 10 miles. But Jupiter's Great Red Spot is 20 times taller.
I think that really brings into perspective the massive scale of this planet.
The dizzying depths of the storm is made possible by Jupiter's vast hidden atmosphere, a seemingly endless spinning mass made up of hydrogen and helium.
Jupiter doesn't have a solid surface like the Earth does. And so right away, if you were to dive into Jupiter's clouds, things are going to be really different. This atmosphere is tremendously thick, so as you're going in, the pressure is going up.
As soon as you start plunging down into that atmosphere, there's more and more. There's not just 100 miles of air, there's 1,000 miles of air, or 10,000 miles of air above you. And all of that massive bulk of Jupiter is squeezing in all that air, so the air pressures and densities skyrocket. Not only would your ears pop deep in the Jovian atmosphere, your entire body would pop, and in fact, all of your molecules would pop. That's how strong these pressures are.
Juno's vast turbulent atmosphere hosts the deepest storm mankind has ever seen. And Juno's discoveries get scientists wondering, could the Great Red Spot be behind another of Jupiter's mysteries, the planet's surprisingly warm atmosphere?
Jupiter lurks out in our outer solar system, where everything is very cold. The sun is very dim when you get that far away.
Jupiter is 5 times farther from the sun than we are, so it's only getting 4% of the amount of energy from the sun that we do.
But there's something heating up the atmosphere of Jupiter. There are parts of it that are many times warmer than we can explain with sunlight.
The question is, of course, where is that energy coming from?
Juno swoops in for another pass on Jupiter, turning its high-resolution cameras on the raging storm below. The storm unleashes vicious turbulence into the surrounding atmosphere, giving scientists the clue they need to explain the planet's high temperature.
The Great Red Spot is a giant hurricane that's powered by heat deep in the core of Jupiter, but it has such violent and chaotic motion, it's mixing up the atmosphere around it.
The thunderstorms on Jupiter are going to be generating booming thunder, just the same way that they do here on the Earth.
Thunderclouds send sound waves rippling through the storm.
A sound wave is a wave of pressure, of compression, where air molecules or water molecules get compacted. They get squeezed together. And when you squeeze something together, they're a lot closer together and they're gonna get pretty hot.
These sound waves shoot up 500 miles above the storm, where they break, converting sound energy into heat.
These sound waves, they crash together, creating a tremendous amount of energy and heating the gases around them.
The Great Red Spot has helped heat the Jovian atmosphere for hundreds of years, but new images suggest that this may be about to change.
Jupiter's red spot is so big. I mean, it's bigger than Earth by a long shot. It seems like it would be an incredibly stable thing. It's just there and it's always been there and it always will be. Recently, we've seen it changing.
When NASA's Voyager space probe visited Jupiter in 1979, it observed a storm twice the diameter of Earth. In 2017, Juno's images show the Great Red Spot has lost 1/3 of its width. But that's not all. Despite the storm's shrinking size, it's actually getting taller. The Great Red Spot is being stretched and forced into Jupiter's upper atmosphere.
The storms in the Great Red Spot is kind of like the clay on a potter's wheel, where as you bring your hands closer together to draw the clay in, the closer your hands are, the taller the pottery becomes. And similarly for the storm, as it becomes smaller at the base, it raises taller toward the upper atmosphere.
It's getting taller, and we see storms do the same thing on Earth, and when it does that, the wind shear will actually take the top of the storm off and drag it apart. And so we'll be watching it very intently over the next few years to see if that's what happens on Jupiter as well.
It may be only a matter of time before Jupiter's high-altitude winds tear the iconic storm to shreds. The most famous storm of our solar system may soon disappear, but Juno reveals other storms hidden in the strangest of places.
The storm in the Great Red Spot is one, but not the only giant storm that's happening on Jupiter.
NASA's Juno probe has voyaged billions of miles across the solar system to reveal the mysteries of gas giant Jupiter. But there's one part of Jupiter that has remained hidden until now.
Before Juno, our view of Jupiter was very limited. We'd never actually flown over the poles.
It's something that's very hard to do on Jupiter. We don't have other missions that have done this.
In August 2016, Juno's flight plan takes the spacecraft into unknown territory to reveal Jupiter's mysterious polar regions for the first time.
When the first time we looked at the pole, it didn't look anything like the Jupiter we knew. We never would have guessed that was Jupiter if somebody had shown that to us.
Juno's camera reveals a strange blue expanse that puzzles scientists. The electric color could be due to chemical changes in the clouds, brought on by a lack of sunlight. But what Juno spots inside the blue clouds is even stranger. Giant central cyclones spin around each pole at 200 miles per hour, with these cyclones surrounded by 8 stormy vortices in the north and 5 in the south.
There are these weird cyclones, gigantic swirls, vortices of gas swirling around Jupiter's poles, and they're clearly forming patterns. It's hard to get a sense of scale here. Now, the North Polar Central Cyclone, that one right at the pole, that's 2,500 miles across. That is almost as big as the continental United States. What is going on there? This is nothing like what we see on Earth.
On Earth, our weather is driven by heat from the sun. It hits our planet at the equator and flows across the surface. Powerful cyclones form over tropical waters and move around the planet. But the polar regions receive less energy from the sun, so cyclones can't form at the poles.
We see that if you're at the equator, it's warmer and it's stormier. If you're at the poles, where the sun is slightly harder to see, that activity goes away.
But the weather on Jupiter couldn't be more different.
We see lightning and convective thunderstorms at the poles of Jupiter, but not at the equator. And that's sort of the opposite of what we see on the Earth.
Question is, what's driving Jupiter storms?
Jupiter is 5 times further away from the sun than the Earth and receives only a fraction of the sun's energy. And unlike Earth, Jupiter's polar regions seem to be where the action is. Something is driving the planet's weird weather, and Juno's scans of the giant planet's thermal emissions suggest it could be Jupiter itself.
We can actually see the internal heat of Jupiter coming right up through. And so Jupiter will look very bright in areas where we can see that heat.
Juno detects searing heat beneath Jupiter's cloud bands.
Jupiter has so much material, so much mass, so much gravity that the interior is incredibly dense and very, very hot. At the core, it's probably many thousands of degrees hotter than the surface of the sun.
This fiery inferno buried in Jupiter's dark heart is a relic from its birth billions of years ago. The violent collisions that formed the planet leave its core seething hot, a heat that remains to this day, buried under thousands of miles of insulating gas. As the heat slowly leaks outwards, Jupiter's fast-rotating atmosphere gets churned up into vicious cyclones and thunderstorms.
And that's what's really driving most of the weather. It's not the sun, it's Jupiter itself.
But there's still a mystery to Jupiter's polar storms. As Juno swings around for another pass, it sees the same storms still going strong.
One of the interesting things about the storms in Jupiter's poles is that there are these arrangements of the vortices that seems to be pretty regular and repeating.
These geometric arrangements are bizarre, but they bear a striking resemblance to another of our solar system's great storms. November 2012. The Cassini spacecraft orbits Saturn's North Pole. It captures incredible images of a bizarre storm raging far below.
When missions first flew over Saturn's pole, they found a giant hexagon.
Saturn's hexagons look too perfect to be formed naturally. But on Earth, scientists use fluid simulations to discover the truth.
When we went back and we tried to recreate Saturn in the lab, it was a structure that was reasonably easy to form. And so that gave us the idea that these sort of structures actually might be quite common in gas giants.
But rather than a simple, smooth geometric shape, Jupiter's North Pole jet stream hosts 8 individual cyclones. These storms should drift to the center and merge into one megacyclone like we see on Saturn. Instead, they appear to be stable.
When 2 cyclones next to each other are kind of spinning in the same direction, they ought to hurt each other, but they don't.
Not only are they not falling apart, but they're falling into these weird, complex patterns that maintain themselves for a long time. What's causing that?
And as Juno soars above the planet, it reveals another weather mystery. The craft detects bursts of radio waves, spiking up to 4 times a second, a telltale sign of ferocious lightning strikes.
clouds are moving around in the atmosphere, building up electric charge, and causing bolts of lightning to form. And we've actually seen this with the Juno spacecraft.
These are megastorms, orders of magnitude bigger than here on Earth.
And Juno finds that there's more to these thunderclouds than just flashes of light. Giant icy hailstones of water and ammonia, the chemical which gives Jupiter's clouds their orange color.
High up in Jupiter's atmosphere, the ammonia is mixing with the water, and it becomes a liquid ball that starts to collect ice around it, and it will fall like hail does, deep into Jupiter's atmosphere.
On Earth, hail falls to the ground, but on Jupiter, there is no ground.
And it gets lifted in the atmosphere because of an updraft, and then more ice, and it builds bigger, and then it falls down, and then it gets carried back up, and so hail is often many layers being built.
These icy balls grow layer by layer as they soar up and down the atmosphere. If they formed in storms here on Earth, they'd cause some serious damage.
So if you were buzzing around Jupiter and you were near where these storms were, you might get hit by hail coming up or going down.
This is one of the most violent, energetic atmospheres in the entire solar system.
Juno is revealing Jupiter's hidden secrets, including the mystery of Jupiter's northern lights.
When Juno studied the lights coming from the aurora on Jupiter, it found that something really weird is going on.
On Earth, dazzling auroras light up the skies as charged particles from the sun interact with atoms high in the atmosphere. Deep in the outer solar system, Jupiter is too far from the sun for strong auroras to form in this way. But high above the giant planet's poles, Juno spots a seemingly impossible light show.
The auroras of Jupiter are tremendously larger than the ones that we find here on Earth. In fact, the auroral rings near the poles are bigger than our planet itself.
Jupiter's auroras emit primarily ultraviolet and X-ray light, so you can't see it with the naked human eye. But if you could see them and you were at Jupiter, that would be an amazing light show, because those auroras are strong.
These glowing displays are evidence of charged particles slamming into Jupiter's atmosphere.
But if they're not coming from the sun, where are they coming from?
Hunting for an answer, Juno snaps an image of Jupiter's southern lights with its ultraviolet imaging spectrometer. Inside the aurora, it glimpses something strange.
When Juno studied the lights coming from the aurora on Jupiter, it found that they were even stronger than expected. And in fact, when you look at Jupiter's poles in wavelengths that our eyes can't see, for example, ultraviolet, you see a hot spot.
This hotspot marks the point where huge concentrations of charged particles strike Jupiter's atmosphere. Tracing their trajectory reveals the culprit of Jupiter's dazzling light shows, the volcanoes of Jupiter's powerful moons.
Jupiter's moon Io has hundreds of active volcanoes spewing out materials way out into space, and many of those get trapped by the magnetic field of Jupiter.
Io's volcanoes fire out jets of charged particles, which are swept up by the giant planet's magnetic field.
It's funneling those particles down and slamming into specific spots in Jupiter's atmosphere.
But Io isn't the only moon responsible for Jupiter's polar light show.
If we go further out, Europa, Ganymede, Callisto, those are more icy, don't necessarily have volcanoes.
These icy moons twist up Jupiter's magnetic field.
Some of these moons have magnetic fields that interact with Jupiter's magnetic field, and that actually intensifies the aurora display on Jupiter.
Jupiter's moons work together to energize the greatest northern lights in the solar system. But in these beautiful displays is a stark reminder of the danger Juno faces.
When you look at these pictures of the aurora on Jupiter and you think, oh, that's beautiful, wouldn't it be great to see that in person? The answer is no. No, it wouldn't, because they will kill you. What's causing these displays are subatomic particles accelerated to tremendously high speeds by the magnetic fields involved.
The radiation around Jupiter is lethal.
The lifetime of the Juno mission is very limited by the extreme conditions it has to survive in. We think that in the future, a lot of the instruments will be so radiated they won't really work anymore.
When Juno's titanium armor fails, Jupiter's deadly radiation will damage the craft beyond repair. So the team plans to go out with a bang, thrusting Juno into Jupiter's atmosphere, where the craft will be torn apart.
Eventually, it'll be drawn down into Jupiter's depths and become a part of the planet itself.
Before then, Juno has many more mysteries to unlock.
We'll answer some questions, and we'll raise some more. That's what I expect. And we'll get some fantastic images.
Every single thing has turned out to be a surprise.
There are so many things that Juno has opened our eyes to that I can't imagine having not sent it.
So we're in for at least a year more of the most profound surprises about Jupiter.
What we're learning, what we're unlocking, not just about Jupiter, but the formation of the solar system and the potential formation of life itself here on Earth. It's mind-blowing.